stand by. We are about to begin. Welcome and thank you for standing by, everyone. All participants will be in listen-only mode throughout today's presentation. As a reminder, today's call is being recorded. I will now turn the meeting over to Mr. Tom Gall. Sir, you may now begin.
Hello, everyone. One note before we start. If you need technical support with Premier functionality at any time during today's webcast, dial *0. With that taken care of, I'd like to welcome you to the first webcast of Emerson Network Power's 2007 Business Continuity Leadership Series. I'm Tom Gall, and I'll be your host. This is our first of 3 webcasts this year, and we hope you'll join us at the same time on June 6th when we'll look at developing cooling strategies to support new technology adoption. Also, our webcast program is certified by the International Association for Continuing Education and Training. So attending a 1-hour webcast qualifies you to earn 1/10 of a CEU training credit. Just check the box in your survey following the webcast, and you'll receive your certificate by mail within 2 to 3 weeks. Today, we'll learn how to take the next step toward business continuity and look at some best practices. This presentation deck will be available to download after the webcast. Check the link in your thank you email. I'll give you a brief introduction of Emerson Network Power and its Liebert solutions. Then we'll move on to our presenters. Slide. Emerson Network Power is an Emerson business and the global leader in enabling business-critical continuity. That means they provide the technology that powers and protects the critical systems businesses depend on, like servers and communications equipment. Emerson Network Power's Liebert solutions empower a dynamic critical infrastructure that helps organizations rapidly address and manage technology changes. This greatly enhances operating flexibility while protecting availability and reducing total costs. Slide. Through their solutions and their service organization, Emerson Network Power helps every company in the Fortune 500 keep its systems running. Here is just a sampling of some of the recognizable organizations who rely on Emerson Network Power to keep their business in business. Emerson Network Power has customers in virtually every industry, including telecommunications, computing, healthcare, transportation, manufacturing, web hosting, and banking and finance. Now a little bit about how our webcast will run. In just a minute, I'll introduce Peter Panfill, who will share some strategies for improving your ability to maintain IT system uptime, despite internal and external threats. Then we'll move on to Carl Shelton, who will share some information on how it's done at the Maui High Performance Computing Center. You can ask questions via email throughout the webcast, and we'll select several to be answered by our speakers during our closing Q&A. To ask a question, click the Q&A tab at the bottom of your screen. Type your question in the box along with your company name and submit it. In case we run out of time during our webcast, we'll follow up on your question via email. Most questions will be answered within 48 hours and technical questions within a few days. Slide. Now on to our first presenter. Peter Panfill is the Vice President of Power Engineering for Liebert Solutions at Emerson Network Power. Welcome, Peter.
Thanks, Tom.
Peter, tell us how we can improve our readiness when it comes to infrastructure systems.
Sure, Tom. I'll start with some basics and move up to some best practices. Slide. Today, we're going to cover causes of interruptions, readiness statistics, analyzing your infrastructure and availability tier levels, a new way to describe availability tiers, moving up the tier levels, and some high availability benchmarks. Slide. Major causes of downtime include software defects and failures, planned administrative downtime, system network reconfiguration and application upgrades, operator error and hardware maintenance, and building and metropolitan area site disasters, fire, explosion, earthquake, tornado, those kinds of things. Slide. Now let's look at some of the threats to infrastructure availability. And when you start to list them, it looks pretty intimidating. Some of these are fairly obvious, such as natural disasters, and some not so obvious, like the impact of external agencies and of new technologies and applications. But with the exception of inadequate service level agreements in external agencies and organizations, there are infrastructure design strategies and technologies you can use to minimize your vulnerability to these threats. Here are some load loss data collected by Liebert Global Services. You can see that more than a third of load loss was caused by insufficient or bad batteries. Add EPO and user errors, and that percentage goes to more than half of all load loss. Slide. Most server manufacturers say that about 40 centigrade is the maximum heat their equipment can stand. After that, shutdown is not your only problem. You're also looking at component degradation. If you lose cooling in a facility where your average rack is about 5 kW, you've got about 25 minutes to address the problem. If your average kilowatts per rack is about 14.5, which we're seeing in some installations today, you've got about 2 minutes. Obviously, this is an issue that needs to be addressed in your business continuity planning if you plan on staying up for more than 2 minutes after cooling loss. Even if you aren't in a high heat density environment, an interruption in cooling can cause a failure. When one major New York area wireless service provider experienced system failure after the blackout of 2003, it was ultimately a cooling issue that brought them down. Though the power system, including batteries and generators, was designed for high availability, the cooling system was not attached to a backup power supply. So when utility power went out, so did cooling. So in just 4 hours, the telecom equipment overheated and failed. On the power side, they actually had enough generator runtime to ride through the 8 hours. So the cooling issues cut their planned ride-through in half. As densities increase, more organizations will experience these types of outages if they don't take preventive measures. Slide. At the end of last year, Emerson Network Power sponsored a survey of readers of Continuity Insights magazine, and here are some of the results of that survey. 76% of the business continuity professionals surveyed do not perform what we would consider to be a real test of those generator systems. 68% don't know how long their computers can operate without cooling. We just saw some of those times to thermal shutdowns earlier. While 44% said their cooling systems are not redundant. 30% don't have monitoring. 27% don't have redundancy in their power systems. So there's definitely a gap in many cases between the availability needs that are required to support business continuity and the systems that are actually employed. Slide. Once you understand your downtime costs, you can start to determine what level of availability and resilience you need and what steps you can take to get there. These are just some of the questions you should ask yourself as you begin to prioritize steps to improve your resilience. Are your line drawings up to date? Has your load been calculated based on real power usage? Do you know if your UPS batteries can still provide the runtime you need? Have you calculated the amount of time your computer systems can operate without cooling? Do you have UPS battery monitoring systems in place and a preventive maintenance program? Assessing your infrastructure is a complex undertaking, and it's important to understand the details of the systems you're assessing. You can go to Liebert.com, and under the Business Continuity topic area, you can link to an availability quick test to get you started. Slide. Now let's look at one of the many availability tiers definitions. This one is from Uptime Institute. The key progression is from a basic system to redundancy, to maintainability, to fault tolerance. These are tenets of most tiers definitions. Let's look at a progression through availability tiers that is model independent, one that focuses on the structures critical to success. Slide. A basic data center is susceptible to disruption from planned and unplanned activity. Maintenance requires total system shutdown, and operational errors or load-generated faults will cause a data center disruption. Slide. A redundant component data center is less susceptible to downtime from planned and unplanned activity, but certain maintenance activities require load shutdown. It has a single critical bus to power distribution. Slide. In a concurrently maintainable data center, planned maintenance can be performed without required equipment shutdown. It has enhanced redundancy design of the UPS and generator system. Typically, the capacity is N+1, and the critical load on the system does not exceed 90% of that N. UPS system maintenance can be performed while still providing UPS power to the load. In this case, operator error can still cause load disruption. Slide. Here is one line of a concurrently maintainable data center. It has redundant feeds, redundant engine gen, and transfer switches with precision cooling on the generator protected source, redundant UPS modules and maintenance bypass, separate power distribution paths to dual-corded loads, but a single critical bus to that distribution. There's a clear path to a fault-tolerant data center from one that is concurrently maintainable. Slide. fault-tolerant data center, the system can sustain one worst-case fault condition without load shutdown. It utilizes bus switches for dual sourcing, single-corded loads, and fault isolation. It is fault-tolerant in that load-generated faults are isolated from affecting the other critical loads. It includes simultaneous active distribution paths, dual bus. Each system has N+1 redundancy, and the combined critical load on the system does not exceed 90% of N, which is typically 40 to 45% on each side. There is still an exposure due to the single point of failure from fire systems and EPO. Slide. Here's a one line of a fault-tolerant data center. Redundant feeds, redundant engine gen and transfer switches with precision cooling on the generator-protected sources, redundant UPS systems, dual critical buses to separate power distribution paths powering dual-corded loads. Static switches are not shown on this one line. They would be between bus A and bus B to power single-corded loads. We're also seeing static switches used for fault isolation as well as feeding dual-corded loads on multiple bus systems. Slide. In climbing the availability ladder, gaining momentum in IT infrastructure are data protection and mirroring, sometimes driven by governance, other times by performance guarantees. On planning and management, it's realistic testing using real-world plans with change control and scope that involves all stakeholders. MOP here means methods of procedure, ones that are routinely reviewed and tailored to the actual configuration being managed. Slide. Drivers to mitigate up and availability classification include elimination of single points of failure, improving maintainability, mitigating that downtime cost, improved redundancy, compartmentalization through zone distribution, and improved fault management. Redundancy can be built at the component level, at the unit level, and at the room level. And critical systems management helps to improve reliability using the systems you already have in place today. Slide. Let's look at eliminating single points of failure in a basic data center. This data center has a single bus, single module UPS, no maintenance bypass, single distribution out to those loads, single cable per computer device, and single power supply per server. A number of single points of failure. Slide. Moving to a fault-tolerant data center, we've added a dual bus redundant module UPS with maintenance bypass, redundant electrical distribution, smart power strips in the racks. These help to eliminate excess cabling under the floor and improve airflow, and dual power supplies per server. All single points of failure are eliminated except for EPO and the fire systems. Slide. Adding redundancy for cooling can be accomplished with the addition of local cooling. You want to take the fluid closest to the heat source, either through coils on the rack, coils in the rack, or fluid directly to the CPU. It has a positive impact on capacity and availability, as well as scalability and total cost of ownership. Slide. Here is a depiction of local cooling using overhead cooling units mounted in the ceiling. High availability methods are used by employing redundant cooling loops. Slide. Here is a depiction of local cooling using overhead cooling units mounted on the rack. Again, redundant cooling loops are employed. Slide. And here is a depiction of local cooling using in-row cooling. In all of these configurations, local cooling supplements base load cooling to help deal with high heat density applications. All use a hot aisle, cold aisle approach. Slide. Let's turn to monitoring. Integrated systems management provides understandable alarms and actions to follow. How many times have you been involved in analyzing an alarm generated by your systems that you do not understand due to its cryptic nature or it's not accompanied by actions to take that are understood by all involved? This is a continuous process with investment in the monitoring system, manpower to manage the data and training. Having predefined actions and responses to incidents helps reduce accidental misoperation. Slide. Here's an example of cooling telemetry. Rather than just being given an overtemp alarm, you're made aware that conditions are warming, giving you a chance to respond before conditions get critical. Slide. Here's an example of UPS telemetry. You could know the power profile of your system prior to any action being taken. This would allow you to identify when out-of-norm conditions occur. Slide. For generators, critical temperatures and peak currents delivered may be of most value to you. Slide. We saw earlier that over a third of critical bus failures were caused by bad batteries or inadequate battery runtime. Capturing battery telemetry is a vital tool to help identify potential problems. Slide. All these contribute to a change from break-fix to predictive monitoring, improving availability. Slide. Now let's do an infrastructure analysis. This was an actual data center that needed to improve its capacity, redundancy, and availability. There were many single points of failure. There was limited adaptability. There was a single UPS reaching full capacity, and the data center was running out of PDU circuit breaker space. Power cable management under the floor was a challenge, and there was limited ability to perform system maintenance. Slide. The project was broken down into business requirements and drivers and solutions. The first requirement was to create a fault-tolerant and high availability infrastructure through the elimination of single points of failure. The solution was to engineer infrastructure to progress from a basic data center to a fault-tolerant one. Increased power capacity was needed to support business growth. A solution was to increase capacity from near full load on a single bus UPS to 40% on a dual bus system. Slide. Increased circuit capacity was needed to support IT growth. The solution was to design dual distribution paths using static switches for single-corded loads and increasing the number of available circuits. The ability to perform preventive maintenance was also a critical addition, without having to put the systems at increased risks of major outage. A dual-bus UPS design allowed for the ability to perform UPS preventive maintenance while operating with dual-bus availability. Slide. Zone power distribution was employed to improve subfloor cable management as well as improve subfloor airflow. A zoned floor plan was created for the power system. Advanced planning allowed new circuit cables to be pre-ordered with the cables according to length. A reduction in cable lengths meant less clutter underneath the floor, and the post-project plan included removal of old power cables to help improve subfloor airflow. Next slide. Improved power circuit manageability involved the real-time view of the power circuits. Additional monitoring was added for the distribution circuits, additional circuit labeling was added, and a facilities database was created to include all systems and their respective circuit ID numbers. Real-time visibility to all power events was necessary. What was installed is a centralized monitoring system. Power systems as well as environmental parameters were added to that monitoring system, and battery monitoring was a part of that overall infrastructure monitoring configuration. Next slide. To ensure that the computer room air conditioners did not lose power in the event of a power loss of one of the critical buses, electrical redundancy was added to the computer room air conditioners. They were mounted post-transfer switch, so the automatic transfer switches would provide protected power to the computer room air conditioners in the event of a power loss. Finally, they wanted to add uninterruptible power to the IDF closets. In this case, they installed UPS systems in the IDF closets, and they were supported from redundant power feeds. The data center consolidation project required additional cooling BTUs to deal with the new blade technology that was being employed in the data center. Spot cooling was used during the upgrade of the outage window. And then the added monitoring capability was required because of enterprise visibility and SOX compliance. A solution was to add page views for remote location monitoring, as well as centralized views for alert for any of the alarms that occurred in the system. Next slide. Let's look at some high availability benchmarks. Here's an example of Cardinal Health drivers to migrate to a fault-tolerant data center. They had a number of company has 2 data centers in the U.S. and has a combined total of more than 100,000 square feet of controlled space. 10% of the world's economy is moving through these 2 data centers at any given moment. Both data centers operate 24 hours a day, 7 days a week, 365 days a year. In addition to these centers, the company has a number of primary telephone rooms, each with distributed floor-level telephone rooms, and then further distributed to numerous network closets. The data centers are both protected by 2 UPS systems. In a 2N system, either one of the two UPS systems could take over the load in case of a failure. Battery backup on each system is 30 minutes of runtime. It is also important to note that all of the company's remote locations, computer rooms, network closets, and telephone closets, are all protected by UPS systems. Redundant cooling systems are also employed. Each redundant cooling unit incorporates two compressors for additional component-level redundancy. An extensive monitoring system provides advanced information on everything from incoming power to temperature in the racks. The data collected is used to prevent failures before they occur. Slide. All system maintenance must be pre-approved before being performed. Once approved, maintenance is conducted between 10 p.m. and 6 a.m. All IT systems must remain running during maintenance. Each piece of equipment has a prescribed preventive maintenance schedule. An automated maintenance management system sends out reminders that maintenance has been scheduled. For security purposes, all rooms are locked and have key card systems for entry. They are also monitored with video surveillance systems. Most large companies have load banks brought in to test generators once or twice a year, but this organization has load banks on site for frequent testing. Once a year, pull-the-plug testing is performed that sends all IT systems to backup generator power. Why is all this done? Slide. No downtime. The company's vigilance has paid huge dividends. In 8 years, it has experienced no downtime in any of its main data centers. This accomplishment is far above industry average, and the company has been able to capitalize on its reliability, and they promote it as a competitive advantage. Slide. Finally, we have a major banking and financial firm. Their facility uses enough power to light Lower Manhattan. The power is protected by 2N UPS systems with maintenance bypass capability, so the organization is always operating with twice the required amount of power for full system protection. By maintaining an extra available UPS and by using static transfer switches, the organization can keep single and dual-corded load equipment fed and with conditioned power at all times. Equipment is cooled by redundant precision cooling systems. All remote applications are protected to 6 nines reliability by incorporating the same online double conversion UPS technology there. Power is monitored from the time it enters the building all the way to the network and computer equipment being powered. Temperature, mechanical issues, humidity, equipment changes, leak detection, and battery life are all monitored. Data is collected and information is used to make preventive repairs and replacements so that failures are avoided. Slide. When we talk about protecting computer systems with redundancy, this isn't just limited anymore to a single data center. Additional redundancy, providing an even higher level of availability, is achieved by having a second or even a third remote backup data center. This practice has become more and more prevalent since September 11th. For physical security, no one can enter a data center, computer room, or even a network closet without being on an approved list or without having proper identification. This practice doesn't just protect against potential sabotage, it also reduces the chance of human error and ensures that only experienced service personnel have access to vital infrastructure. Another key procedure often taken for granted is to consistently label and document all components, patch panels, and cables to avoid pulling the wrong handle type mistakes. Carefully maintained up-to-date system drawings are always on hand in each data center. Sufficient fuel for the backup generators is stored for a 30-day supply. Yes, you heard that right, a 30-day supply with well-executed contracts in place to maintain and replace it. The fuel is also tested regularly to detect contamination. Slide. This company is so confident in its ability to generate backup power that in exchange for reduced utility rates, they've negotiated a contract with Con Ed to go off-grid and generate their own power up to 8 times a year in cases where Con Ed has experienced a spike in demand. The following quote is directly from the company's Statement of Disaster Preparedness. Our effective response to an electrical blackout that affected most of the Northeast United States, including New York City's financial district, clearly demonstrates the effectiveness of our response to disruptive events. Slide. In summary, tier systems are useful guidelines but have limitations and standards. Use your availability needs as a guide to move your data center up the availability tiers from basic to redundant to concurrently maintainable to fault tolerant. Your actual availability depends on your design and your operations. You can safely and effectively increase your tier availability, and integrated systems management helps you to optimize your availability by getting the most out of what you have now. Business strategy drives availability needs, and availability needs drive design and operation. That wraps up my portion of the presentation today. I'll turn it over to you, Tom.
Thanks, Peter. I'm sure our attendees will find some immediate action steps in what you've shared with us today. Now on to our second presenter. Carl Shelton is with the Maui High Performance Computing Center. Thanks for being with us, Carl.
Hey, I'm pleased to be here.
Well, Carl, tell us a little bit about how you protect your critical systems in Maui.
Well, we have a world-class computer center here with a lot of service agreements and an absolute need to stay perpetually up and running. And so we have some unique, especially infrastructure needs, and a lot of thought went into the requirements that we would have here. And we just say that anybody's getting ready to build one of these things, their mantra ought to be infrastructure first. Next slide. We're here at the Maui High Performance Computing Center. We're operated by the University of Hawaii in Maui, and we're part of the Air Force Maui Optical and Supercomputing Amos site, where we perform a lot of vital defense and scientific research functions. Next slide. Just to try to impress you a bit about what we do here as one of the world's fastest supercomputer sites. So we have a terascale performance computing platform as one of our supercomputers with a 5,120 processor array based on Dell PowerEdge servers, which processes 60 teraflop floating point operations per second. Next slide. As our high performance demands high availability, our high performance computing is just our sole mission. That's the only thing we do. With more than 21 million hours of computing time annually. Our critical nature of research requires that we remain up and running 24 hours a day, 7 days a week, 365 days a year. We just cannot afford to ever go down. Next slide. And as part of the challenge that we face here, we're in a difficult location. We are isolated out on an island. It's an area that's prone to tropical storms, earthquakes, physically remote, with a single public utility providing power for us. We're not on a grid with multiple utility systems or a grid interconnected into several cities or several states or anything like that. We have a single source of power, which is Maui Electric. Next slide. In planning for our continuity, our business continuity plan is pretty simple. We plan to stay up and running and supporting our systems 24 hours a day, 365 days a year. And that's just absolute mission critical that we accomplish that. During any loss of power due to severe weather, we remain up and running our computer systems. Some of our people may not be here to accomplish much, but our computing systems stay up and running. And our center continues in operation, and MHCC has invested in a dynamic, critical physical infrastructure to accomplish that continuous operation. A lot of planning and effort went into the infrastructure to accommodate what our systems demand. Part of our critical physical infrastructure is our room arrangement, the configuration of how we set things up, our precision cooling, our backup power, and our power distribution systems. Next slide. Our room configuration for our primary supercomputer is 40 racks in 4 rows set up in a hot aisle, cold aisle configuration. And one of the things that we were pretty smart in doing was putting in a 36-inch raised floor, which sure does help with the cooling. It prevents a lot of turbulence under the floor and makes it a lot easier to keep things cool in the data center. Next slide. Our precision cooling consists basically of 12 Liebert Deluxe computer room air conditioning units located perpendicular to the ends of the aisles. It provides 360 tons of cooling, as well as humidity control and air filtration, which the humidity control and the air filtration is a real critical element that those systems provide for us, and that's backed up by some Liebert chillers connected to the building chill water system. Next slide. Our backup power is a separate power distribution room is where we operate that from. We also have a 1.5 megawatt generator, multi-mode Liebert Series 610 UPSs with 900 kVA combined capacity, which will expand soon to 1350, configured for 15 minutes of backup time before switching to the generator, which we've tested, and it actually will last 15 minutes, although with our generator kicking in, it typically only is required to last a few seconds until our generator gets up to speed. And it's all connected through a Liebert system control cabinet. Next slide. Our power distribution now is 4 Liebert precision power centers, provide grounding, custom electrical distribution, monitoring, and expansion capabilities. And that's a really nice feature that anybody building a new data center ought to really consider. That makes monitoring and knowing what's going on at all times really convenient and handy. Our monitoring and preventative maintenance on the next slide there has built-in display panels which allow our staff to routinely check performance of our equipment. Our equipment is maintained by the business of Emerson Network Power with a guaranteed 24-hour response time. And that's a real critical element for us, being out here isolated where we are out in the middle of the Pacific, on not on the main island, but on Maui. Our help when we need it comes from a fellow named Richard Ligori, which works for Emerson. Very knowledgeable, very responsive. If we have a question, he answers it for us. If we ever have any problems, he's right on it. He's on the next plane over here, and we're real happy with the kind of response we get from Emerson whenever we have a problem or a question. Next slide. Again, getting back to our infrastructure and our physical location here, we're located in an area that's subject to earthquakes, to hurricanes, to damage from severe weather, and here recently, late last year, we had a 6.7 magnitude earthquake, which caused a couple $100 million of damage throughout the islands. And MHPCC lost commercial power for about 10 hours. And during that time, our UPS and generators kicked in seamlessly. We had no knowledge of the power outage at all until our operators in the building went outside and noticed that the power was out. They recognized that they had a bit of an earthquake with the shaking and the like, but our equipment all worked just great. Didn't lose a moment of operation. Our research and all our computing needs continued without interruption. Next slide. As a result of our continuous operation, we've got a lot of accolades for that, and we've accomplished that task with the help of a lot of engineers and a lot of thought going into our power and cooling, and we've been able to accomplish that for 10 to 12 years now without any interruption. What it provides for us is a great deal of peace of mind, and our delivery of systems is renowned for its reliability and availability, and that's sort of a testament to not only the equipment, but the people that we have here and the service response times that we get through Emerson. We have a dynamic systematic architecture which enables continued expansion without abandoning initial investments. And again, if you're thinking of building one of these things, a new data center, again, your mantra ought to be infrastructure first. What we've been able to accomplish here is we intend in the next year or so to actually double the size of our computing power, and we'll be able to accomplish that without ever shutting down anything. We'll simply continue to add on power and air, and continue operations while we accomplish that. Next slide. As we look into the future, the supercomputing array that we have now will increase to somewhere in the neighborhood of 120 teraflops, which is just an unimaginable number. Supercomputing that we do here is just incredible. We have a dynamic physical infrastructure designed to expand with our computer systems, and again, we'll be able to accomplish that without ever shutting down. We'll continue to almost double in size and never miss a beat. And a lot of thought went into that and how to accomplish that, and it looks like we'll be able to do it pretty seamlessly. I think that just about wraps things up, so I appreciate your indulgence and your patience with me, and I'll turn it back over to Tom now.
Thanks, Carl. Very interesting. We appreciate you taking the time to be with us today. Well, we received a number of questions from you, and we'll answer as many as we can right now. But remember, the first 50 registered attendees to fill out the brief survey at the end of our webcast will receive a multi-port USB hub, and one lucky participant will receive an iPod Nano. To get to that survey, please click on the survey link on the last slide. By the way, we still can accept your questions, which you can submit by clicking the Q&A tab at the bottom of your screen and typing your question in the box. So our first question comes from Gene at an Ohio bank. Where can I get worksheets to help me begin to measure good data center metrics? I'm looking to change the reactive management and migrate to proactive professional management. And we're going to direct this to you, Peter. Any way Liebert can help Gene with his request?
That's a good question. We'd like to follow up with Gene on that. One of the things that we can work with Gene on is to help him do a business continuity assessment. It's an assessment that helps him determine how he can best utilize the equipment and infrastructure facilities that he already has in place.
Very good. Gene, I hope that helps you. Next question comes from Barry, who works for a consulting firm in Chicago. Where do you get the most bang for your buck when it comes to improving availability? We need to improve our availability, but, of course, we're working on a limited budget. Peter, I'm going to direct this to you as well.
I have a true appreciation for working on limited budgets. I think we all are. I cannot stress enough to keep your documentation, your operating procedures, and your change procedures up to date. These are low-cost efforts you want to do regardless of your data center configuration. The other thing is perform real-world testing. Again, this has a low impact when you make it a part of your operations routine. And do that availability quick test. This will help you focus on if there's additional hardware changes that are warranted. And I will always stress that your primary focus would be on eliminating single points of failure.
Carl, can you add anything to that from your perspective in Maui?
Yeah, that single point of failure issue is something to give some strong consideration to when you're planning anything. Again, I'm one of those infrastructure first kind of guys.
All right. Next question from Michael at a power company in Nevada. What's the most common business continuity mistake you see in data centers? And what's the most common outside threat? Peter?
Well, I would have to say that a fairly common blind spot we see is failing to adequately anticipate your future growth. It's not so much that you don't know what's going to happen in the future. It is that applications come up that you hadn't put into your existing planning that you have to deal with on an on-the-spot basis. It's tempting to size your UPS and cooling system to an initial load and then add modules as the load increases or the applications increase in their heat density. But this has the potential for reduced reliability and increasing your costs in the future. We advocate sizing the initial UPS module no less than about a third of the projected load. That gives you some built-in expandability without compromising any reliability. The most common outside threat, I would have to say, is from the utility itself. We are seeing more and more unpredictable utility reaction and response. And so as much as you can insulate yourself from utility aberrations, the better off you'll be.
This question comes from Scott, and he didn't cite any company. This is directed to you, Carl. It says, Mr. Shelton, in your data center, there appear to be perforated tabs in the hot aisle and along the ends of rows. Is there a specific reason for this configuration?
Yeah, right now we've got a changing heat load, and we're kind of doing a little of the experimenting with the perforated floor tiles. We're just moving air around at the moment and trying to distinguish what would be the best way of blowing air through the floor, and experimenting with some above ceiling airflow also. So it's just sort of a little experiment we're going through right at the moment.
Have you done any in progress check on that yet, Carl?
That's underway right at the moment.
Okay, great. Next question. This is from John at a university on the East Coast. How do you make the case to manage How do you make the case to management that such comprehensive infrastructure is needed? Carl, let's follow up on that one.
Well, of course, dollars are always an issue, but in my opinion, throughout the entire planning process, infrastructure is a critical issue. I would suggest being a strong, positive influence while planning for a data center. And during that planning process, I would simply make an assessment about just how critical the load is and what the consequences of having any downtime would be. Simply making sure that management is fully aware of what the benefits and risks involved are of various infrastructure features. You can go through them one at a time and try to quantify them the best you can in dollars and cents, floor and ceiling heights, backup power, cooling capabilities, expandability, redundancy, all those kind of things. If you can identify, if you have 4 hours of downtime, what does that cost you? If it costs you $100,000 an hour, there's $400,000, and can you afford that, or would investing $400,000 in infrastructure be of benefit to you? In our case, infrastructure was critical. We just simply don't accommodate downtime. We cannot afford it. We have to be up and running perpetually. So infrastructure for us is a critical issue. And when it comes to redundancy, just get all of that you can. And with when it comes to expandability, the nature of information processing nowadays, things change so rapidly that planning is just a perpetual process. And be ready to expand or add cooling, add power, add whatever requirements come down the pike, and it's very difficult to contemplate what those requirements may be. But all I can do is suggest you do your best and be hopeful that you get the best for your buck and the best you can get out of any infrastructure that you can afford to install.
Well, we can tell that you are certainly passionate about infrastructure. Thank you. This is to you, Peter. This is from Ken, who works for a semiconductor company. How popular is the use of flywheels instead of batteries? Would you still need batteries if you use flywheels?
That's a great question. Flywheels are being employed more and more in applications where you have frequent short utility problems. Because batteries are really, their life is impacted by the number of times that energy is drawn from them, the fewer hits that you can put onto the battery, the better off you are. And so what we see more and more is applications where data centers are using flywheels as a bridge between their loss of utility and their generator system firing up. They also have employed a battery set that is a backup also to their generator set. So in this case, they've got a flywheel, a battery set, and a generator set. Again, redundancy at a component level to help give them energy storage. Their flywheel helps them ride through those short-term utility hits. If the generator doesn't kick on, which can happen at times, then they know that they have a certain amount of battery runtime because they've already gone through and determined how long their data center can run on the batteries that they have. And so they have protection after protection after protection to help them protect it through those downtimes.
Great. Very comprehensive. We appreciate that. Peter, keep hot here, buddy. This is from Lloyd, who has no reference to a company. Why do you recommend loading the system to only 40% while leaving 60% spare ongoing?
Well, that 40% that I was referring to was in a dual bus architecture. In that configuration, you would have one bus that would be loaded at 40%, the second bus loaded at 40% as well. This allows you to completely move loads from one bus onto the other bus. So 40% load on one side, 40% load on the other side allows you to move onto one side and have 80% loading. Now, I have been talking to customers recently, and I have heard them pushing that 40% up to 45%, which would be 90% in a single bus application. This still gives you some room in terms of being able to deal with additions of applications without having to expand your capacity, but that 40% really was defined as that 40% was defined as on one bus of a dual bus architecture.
Great, thank you, Peter. Here's going to be a question from Gary, who works for a large construction company out in Fort Worth. And Peter, they're asking for you. Are there any new technologies on the horizon in this area we're discussing today?
Well, we're continuing to design compact rack-based UPS modules that meet the requirements of high-density racks and rooms. It wasn't too long ago that the high end of our rack-mounted UPS range was 3 kVA. Now it's 10 kVA or even higher capacities on the horizon. In larger units, we're moving toward rack form factor UPS modules to provide a greater application flexibility. We've also introduced a new way to dynamically adjust UPS capacity without adding additional hardware, and we call that soft scale. We've also seen some pretty dramatic changes in distribution technology. That distribution technology is evolving because customers are requiring more poles with larger branch distribution breakers to support the increasing number of high-density devices that they're adding to their data centers.
Carl, we have a question for you now. This is from Jim, who doesn't designate a company either. What tiering or equivalent level have you built toward, and has this been certified?
We're presently at about an N+2. It has not been certified, but we're making progress towards that. And
here's a question for you too, Carl. You're on a roll now. This is from Adam at an engineering firm in New York State. You said your operators didn't know about an earthquake until someone told them. He wants to know if you're underground.
No, we're not underground, but we're over here on Maui at the base of a volcano, and we're essentially sitting on solid rock. And they're doing some construction work nearby where they're doing a lot of blasting, so our operators are accustomed to feeling a little shaking now and then.
Besides the coffee, right? Is it?
Yeah.
Well, Carl, he also wants to know what physical protections have you put in place for the data center because of those tremors that may come from time to time?
Primarily, we've met whatever code requirements are for the earthquake zones that we're in, tsunami zones, that kind of thing. We're subject to hurricanes here, so we get some pretty severe weather. And the way we accommodate that is basically through redundancy. By God, if you don't have redundant systems, we'd be in a world of trouble.
Yes, and that comes from the Department of Redundancy Department, too. Peter, back to you. This is from Steve, and he must be a freelancer as well. I see that the overhead XD works better than traditional units. What's your thought on this?
The overhead XD unit has an advantage in that it is only dealing with the sensible heat that's being produced right there at the top of that cold aisle. And so it doesn't have to deal with that base level of cooling and air filtration and humidification management that you heard Carl talk about in his presentation. And so it can deal very effectively and very efficiently with the heat that's being generated right there in that high-density rack. In that configuration, what would happen is the base level cooling would cool, let's say, the lower portion of the rack, and as the cold air runs out, that supplemental cooling system would cool the top end of the rack and keep you from having vulnerable servers there in the rack.
Well, Paul, and thank you very much, Paul. And Carl, I'm sorry to say that we'll need to wrap up the questions right now. But if we didn't happen to catch yours during this webcast, we will have one of our experts answer your questions via email. And remember, the slides will be available to download after the webcast, so your colleagues can view today's session on demand beginning Thursday at www.liebert.com. Don't forget to register for our next Leadership Series webcast, which will be June 6th at 4 p.m. Eastern Time. At that session, we'll look at developing cooling strategies to support new technology adoption. And watch previous webcasts at your leisure by going to Liebert.com and clicking on the Events tab under Webcasts. You can also get audio podcasts under the Events area of our site. If you happen to miss the survey, simply cut and paste this URL into your browser to qualify to win a multi-port USB hub and iPod Nano. On behalf of Emerson Network Power, I'd like to thank you for all of your time and attention today. And if you like today's webcast, we hope to see you again in June. Until then, stay cool, everyone.
Once again, everyone, this will conclude today's program. We thank you for joining us. Please enjoy the rest of your day.